Hello there, young students of chemistry. This is a quick recording to talk about how to write formulas for compounds. So you're given a compound formula, you're given a name of a compound, and what you're going to do is write the formula from the name. Please remember that a formula has symbols and subscripts. Symbols tell us what elements are in the formula. Subscripts tell us how many of each of those elements are present. So we're going to be looking at names and writing the formula. For example, there SO3 says there's a sulfur and 3 oxygens in the formula for sulfur trioxide. Now, there are some compounds that contain polyatomic ions. You have these on a pink sheet or a colored piece of paper that I have provided for you. You need to memorize these formulas for the polyatomic ions and the charge. And here are some rules to help you if you look at them about 8s and ites. One thing that you might want to remember about ions is that if you remember the 8, know that the ite, the 8 has more oxygens than the ite, and the hypoites have less oxygen than the ites. So the per, if you have a prefix of per, that has more oxygen than the 8. And then finally, the one that has the least amount of oxygen are the ides, right? Those are our monoatomic ions. So it goes the prefix per on the polyatomic ion has more oxygens than the 8, which has more oxygens than the ite, which has more oxygens than the hypo, which has more oxygens than the ide. These are prefixes. These others are suffixes. So you're going to need to just read through these notes and then memorize your ions. And then we know that things bond the same way in some families that are in the similar family. So I would expect you to look at silicon and know that silicon's in the same family as carbon. So the carbonate ion will tell us the silicate ion, SiO3 2-, whereas carbonate is CO3 2-. Bromium's in the same family as chlorine, and you have the ion on your paper chlorate, so I would expect you to know that bromate is BrO3-. And then I would expect you to be able to look at a formula IO3- and know that that is iodate ion. Okay, so on to some nomenclature here. When we are writing compound formulas, we need to classify those compounds in 2 ways. The first way is that we need to classify them as either binary or ternary, and the second way is that we need to classify them as either ionic or covalent. You learned in Unit 2 that ionic compounds, we can use a rule of thumb. If they start with a metal, that compound is classified as ionic. If it starts with a nonmetal, that compound is classified as covalent. So here's the stuff that is like it just boils down to. If it is ionic, charges become subscripts. Charges become subscripts. If it's covalent, we get our subscripts from these prefixes. Now, if a compound is binary or ternary, it'd be nice if you knew the definition of binary. Binary means 2, so here we're talking about 2 elements. Ternary means more than 2. Ternary compounds are always ionic because they contain a polyatomic ion. Okay, so when we're looking at a name, the way we can classify binary compounds, all binary compounds are going to end in the suffix "-ide". If it ends in "-ide", it is binary. If it ends in ate or ite, then it's going to be ternary. Okay? So to make the compound electrically neutral, what we're going to do is consider, okay, what are the charges? What is the common factor between the charges? And how many of each ion do I need to achieve that number of electrons that are being transferred? So I think the best thing here is that once you have the notes and kind of thought about them a little bit, let's just do some. Now, we learned last unit that we can get charges of ions from the periodic table because the atoms will bond so that they can fill their S and P sublevels. The S sublevel having 2 electrons, the P having 6, 2 plus 6 is 8. That gives us a very stable electron configuration, that of a noble gas. So all we have to do to get the charges of the ions is to count to the nearest noble gas and see whether the atom needs to gain or lose electrons to achieve that electron configuration. So if we consider family 1 and we look at sodium, for example, the nearest noble gas to sodium is neon over here, number 10. Sodium needs to lose 1 electron to be isoelectronic with neon, so that means that sodium's charge when it bonds is going to be 1 plus. That's true for the entire family. Elements in the same family will bond the same way. If we consider magnesium, the nearest noble gas to magnesium is also neon. So magnesium needs to lose 2 electrons to be isoelectronic with neon. So that entire family is going to form a charge of 2 plus if it's bonding ionically. And because it's a metal, we know it's typically going to bond ionically. So following that thought through, aluminum, 13 electrons there. The nearest noble gas is neon, so it's going to lose 3, which means it will have a 3 plus charge. The carbon family is a little weird. It's generally going to be minus 4 if it's going to bond ionically, and that's mostly with just carbide or carbon compounds where you'd have a metal and carbon. Nitrogen with 7 electrons to be like a noble gas is going to have to gain 3 electrons. So that will form a -3 charge. And then we can follow through with a -2, -1. This is where we're going to get the charges for the representative elements. That would be anything that is not D block. Now for the D block elements, they form more than one charge. For example, iron can form a 2 plus charge or a 3 plus charge. So for right now, we're going to get the charge from the name, and it'll be written in Roman numerals. So it will say iron, Roman numeral 2, or iron, Roman numeral 3. There are 2 elements in the D block that will not do this, and that is zinc, which will have a 2 plus charge always. It only forms 1 ion, so there's no need to indicate which ion it is. And silver is the same thing. It only forms 1 ion, so because of that, we do not have to tell anybody what the charge of the ion is. There's a couple of metals that are not transition metals, but form more than 1 ion. By the way, we call those multivalent. Multivalent means there are many different numbers of valence of electrons there. So tin and lead will also have Roman numerals on them as well. Okay, I think it's best to just get started here. I'm going to do a couple with you and then leave you to follow the rules and do them yourself. So if we look at the first compound, the first thing we want to do is we want to identify it. We want to classify the compound as either binary or ternary. And if it is binary, we're going to classify it as ionic or covalent. Another word for covalent is molecular. So this compound ends in "ide." So we know that it's binary.
Students, if you are assigned to Friday school today, we're asking you to please report to the cafeteria at this time. All students
So all compounds that end in the suffix IDE are binary. Compounds that end in the suffix ATE or ITE are ternary. So we know here that this is ternary. All ternary compounds contain a polyatomic ion, so it's automatically ionic, ionic. This is binary, and sulfur is a metal, a nonmetal. And because of that, that means that this is a binary covalent compound, or binary molecular, however you want to say that. We have another ide here, bromide. Because it ends in ide, we know it's binary. And because barium is a metal, we know that it is ionic. Fluoride means that it is binary. Tin is a metal, so we know that this is binary ionic. Oxide means it's binary. And magnesium is a metal, so we know that that compound is ionic. So this is what we know. If the compound is ionic, this one, this one, this one, this one, we're going to get the subscripts of the formula from the charges of the ions. So let's think about these ions and what their formulas, what their charges are. So iron is, the symbol is Fe, and they're telling us right here that the charge is +3. Carbonate is a polyatomic ion. You're going to memorize this and put it in your steel trap. And the formula for carbonate is CO3, and its charge is 2-. So we know that the number of electrons lost by the iron must equal the number of electrons gained by the carbonate. And right now they don't. So the common factor between 3 and 2 is a common factor of 6. So we need 6 electrons to be lost from the iron and 6 to be gained by the carbonate. So in order to figure out how many irons we need in the compound, we're just going to do 6 divided by 3. 6 divided by 3 is 2. That's the subscript of the iron. And then we need to know, okay, this is the carbonate ion. We can't change that formula. That has to stay CO3. And then the question just becomes, are we going to put a subscript on that? Do we need more than one carbonate ion? And it turns out we do. So we're going to do 6 divided by -2, or divided by 2, which is going to tell us, hey, we need 3 of those. And there's the formula for iron-free carbonate, Fe2CO3. Barium bromide is also ionic, so we'll use the charges to get the subscripts. If you go back to your periodic table and find barium on your periodic table, it is right here, number 56. We know that its charge is +2. We would go and find bromine, right? Bromide came from bromine on your periodic table, and we can see that that is right here. The charge of a bromide ion is -1. So we know that bromide is -1. We know that the number of electrons transferred must equal each other, and now they don't. The barium's losing 2 and the bromine's gaining 1. So the common factor here is 2. The subscripts come from the number of ions we need to make that compound electrically neutral. So to find the number of bariums, we'll do +2 divided by the charge of barium, 2, which is going to give us 1 barium. Bromine has a charge of -1, and then we're going to do 2 divided by the -1 of bromine tells us we're going to need 2 bromide ions to make this compound neutral. Tin 2 fluoride. Tin is a transition metal, and because it can form more than one charge, we have been provided what the charge of the tin is. So the symbol for tin is Sn, the charge is 2 plus. If you look on your periodic table for fluoride, you'll see it's -1. The common factor here is a factor of 2. To find out the subscript of tin, we'll do 2 divided by 2, which gives us 1. And typically in chemistry, we don't write ones. And then if we want to know how many fluorines, we'll do 2 divided by 1. That's 2. Now you may have noticed at this point, and I hope you have, that the charge of the cation becomes the subscript of the anion. And the charge of the anion becomes the subscript of the cation. Do it again with the bromide. The charge of the anion becomes the subscript of the cation. The charge of the cation becomes the subscript of the anion. So this is called crisscrossing charges, and it generally works. It's a quick little way to get a formula. However, if we look at the example here from magnesium oxide, magnesium's charge is 2 plus on the periodic table. Oxygen is 2 minus. So you might be tempted to say that the formula for magnesium oxide is Mg2O2. But that is not the case, because we do not need 2 magnesiums to cancel the charge of 2 oxygens. Here we'd have 4 electrons transferred, and that's not what's happening. Magnesium is transferring 2 electrons. Oxygen is gaining 2 electrons from the magnesium, and because they're already equal, we do not need a subscript. So it's going to be 1 magnesium transferring 2 electrons to 1 oxygen. Let's go back up to our covalent compound. Remember that ionic compound subscripts come from charges of ions. Covalent compounds, subscripts come from prefixes. Subscripts come from prefixes. Ionic compounds, subscripts from charges. So let's go back to our covalent compound. We see that we have sulfur with no subscript written out here. Not subscript, sorry, with no prefix, which tells us that the subscript is known to be 1. We have the prefix here tri. Tri stands for 3. So what they're saying is, by saying trioxide, they're saying, hey, that's 3 oxygens. This is sulfur trioxide gas. Be careful not to slip into thinking that that is sulfite ion. It's not an ion at all. It would have the word ion if it were an ion. This is sulfur trioxide gas, which is different from the sulfite ion. I'm just going to do a few more with you, and then you can do the rest of them on your own. So sulfur hexafluoride, it ends in "ide." So we learned that we need to classify that, and that is binary. Sulfur is a nonmetal. That is covalently bonded. It ends in "ate." That is ternary. Contains a polyatomic ion. Ide is binary. Phosphorus is a nonmetal. So that is binary and covalently bonded. Potassium nitrite, ITE. That is ternary. It contains a polyatomic ion. And then we have ide, which would indicate binary, but be careful here. There is one positive polyatomic ion that I want you to know right now, and that is the ammonium ion, NH4+. You kind of need to get an eye out for the ammonium ion. So this is a ternary compound. Even though it ends in ide, I know there's like all these little exceptions, but you'll get comfortable with it the more you practice. I will say, though, that you have to practice. So remember that if the compound is covalent, like our first one here, subscripts come from prefixes. With no prefix on sulfur, we assume 1. Fluorine is what the sulfur is bonded to, and that hexa means that the subscript on the fluorine is 6. The ternary compound, aluminum acetate, ternary compounds are ionic, so subscripts come from charges. Subscripts come here on the covalent from the prefixes, right? So we need the charge of the aluminum, which you'll get from your tool for your mind, your periodic table. And then acetate is C2H3O2. And the charge of that is -1. You're going to have to memorize that ion. So with +3 and -1, the aluminum is going to have the subscript that is the charge of the acetate. So this 1 becomes the subscript of aluminum, and we don't write it. And then we put acetate in parentheses. Because we need more than 1 acetate, our charges tell us that we need 3 acetates. So we're going to put a subscript of 3 outside of the parentheses on the acetate. The next example is covalent. For covalent compounds, subscripts come from prefixes. Phosphorus symbol is P. The prefix di means 2. So 2 phosphorus atoms. Sulfide stands for sulfur. No prefix. It really should have a mono there, but no prefix means there's only 1. All ternary compounds are ionic, so we're going to get subscripts from charges. The charge of potassium is 1. Nitrite is a polyatomic ion, NO3 with a -1 charge. So when the charges are the same, whether they're 1 and 1, or 2 and 2, or 3 and 3, and 4 and 4, those charges are going to cancel each other out. We only need 1 of each of those ions to have electrons transferred equal each other. So potassium is going to have a subscript of 1. Nitrite is going to have a subscript of 1. And notice that because I'm not putting another subscript on it, I'm not putting it in parentheses. Ammonium has a charge of +1. Chloride is -1. We need 1 ammonium, so I'm not going to put that in parentheses. But I'm also not going to change the formula for ammonium. The formula for a polyatomic ion may never be altered. And then Cl, ammonium chloride. Okay, I hope this has been helpful. You should practice the rest of them that are in your notes. You have note pages that go with this. And let me know if you have any questions. Thanks.